Okay, so the question we got here, how to find the derivative of a function. Well, first we got to think about like what even is a derivative? A derivative a derivative is a function that tells us the slope of a tangent line of another of the function that is its integral. So I'll write it as like tells us slope of tangent line at or yeah. Now what is a tangent line? A tangent line is basically like, let's say we have a curve here. A tangent line is like, you know, when people say, oh, I'm gonna go off on a tangent, it's kind of like they're going off path. So let's say we have a tangent line at the top here. The tangent line is just like a flat line that pretty much matches like the point that it's taken a tangent of. So you see here on the top of this curve, you would have like a pretty much flat line. If you were to take a tangent line here, it would be a diagonal line. The derivative tells us the slope. So that's the run, that's the rise, and slope equals rise divided by run. Okay. Another way that we can see tangent line or the slope of a tangent line, it can also tell us the instantaneous rate of change. So another way you can look at this is like, you know, try this on your own. Go on to like Desmos or whatever graphing calculator you like. Make any function, make it a curvy function you like, but any function, if you zoom in, like really zoom in, it pretty much looks flat. And we're basically taking the derivative means at a certain point we're going to want to you know, find the slope of that area that is pretty much flat when you really zoom in. Okay, so let's say we have a line here. How would we find the slope of this? Well, we would take like, if this is our x axis and this is our y axis, let's say here we have like x of a, and if we call that h, or if we call this distance h, and this is h plus x of a, like you see, like originally we have x of a, go shift over by h and you got h plus x of a. Yeah, so here we have like f of x of a, the result of when you send it through a function, and here we have f of x of a plus h. We're looking for the slope, right? Slope equal to rise over run. Okay, what's the rise? How much does it move vertically? Well, the rise is just like its a final value minus its initial value. So we have f of x of a plus h minus f of x of a. I'm using x of a because like I don't want that to be confused with the x-axis. But like you do see in here, they just use x, but that is not, that doesn't really change much. And on the bottom of this little fraction that we got, we have its destination where it ends up divided by or minus where it came from. So we have h plus x of a minus where it started from, and that's just x of a. These two terms zero each other out. So we know that the slope is equal to f of x of a plus h minus f of an x value that we sub in at and all of that is divided by h. Okay, so that's how it seems like on a macroscopic scale. But we really want to be zooming in to get as accurate as possible, because like the more you're zoomed out, the less that you can approximate your functions to be straight lines. Only when you like really zoom in, meaning that our h value here has to be really small, and then we can calculate this out. So let's say that we were to we got to find out a way that we can kind of see what this is going to approach as h gets closer and closer to 0. So typically when you're learning calculus, you learn about limits, right? So this is why limits are important. So we want to minimize h. And we're going to do something like this. So we got to find out what the slope is by doing the limit of h as h approaches 0, meaning h is getting super small, and we are getting like a more and more accurate calculation for our slope at that point. So we have f of x of a plus h minus f of x of a all over h as h approaches 0. So this is the definition of a derivative, and that's where it comes from. It's like we're trying to find the slope, and we know our slope equation, and then we want to get this such that to be as accurate as possible, we want h to be like closer to 0. Okay, so let's run this through an example. Let's say that we have f of x. Let's see if we can match the example that they give us. It is 2x squared plus 10x. Plus 10x. So let's sub this into our equation. Instead of using a specific value for x, which would be like an x of a, let's just use a general x. So I'll actually just like erase the subscript a that we have here to specify that would be like a specific x, because if we're trying to find the derivative at a certain point, let's say the derivative at x equals 5, we would sub in like x of a is 5. But instead, we're just going to keep it as a general x. Okay, so what would be f of x plus h? Well, for every time we see x, we're going to put x plus h. That first one is squared. The second one plus 10x plus h. Let's expand this out. F of x plus h. So that's 2 times x squared plus 2xh plus h squared. Right? So multiply that by itself. Add up 2 times, first times second, and then add up the second one squared. And this the next term that we got here, 10 times x plus h, so that's just 10x plus 10h. And let's expand out this first little section that we have here. So that's 2x squared plus 4xh plus 2h squared plus 10x plus 10h is equal to f of x plus h. Okay, now that looks long, but it should not look scary. So we have our f of x plus h, we have our f of x, and h is just what we're going to leave in h. So let's sub all of those into the equation and see where that takes us. Limit x approaches, oops, it's not x approaches, h approaches 0, because we still need x because we need to find derivatives at certain points. The derivative is just going to give us an equation to help us find the slope, but we need to sub in an x value to get the slope at certain values. So the first thing that we have here is 2x squared plus 4xh plus 2h squared plus 10x plus 10h minus the original f of x. We have to put that in brackets. 2x squared plus 10x. All of that over h. Okay, so let's do some quick math to see what we can cancel out. So let's send this this negative 1. Let's just copy this real quick. Okay. So what I did here is I multiplied those last two terms by negative 1. Okay, and you see, okay, we have a negative 2x squared and a positive 2x squared. So those zero each other out. We have a positive 10x squared and a negative 10x squared. So those zero each other out as well. So let's see what we have left that is not zeroed out. Limit h approaches 0. 4xh, that was not zeroed out, plus 2h squared, also not zeroed out, plus 10. 10h, that was not zeroed out, all divided by h. If we look at the top, all three of these terms multiplied by h. How about we factor that out? H approaches 0. We have h 4x plus 2h plus 10h. All divided by h. Oh, look at that. We got h on the top, h on the bottom. Divide them out of each other. And we have limit of h approach 0 of simply 4x plus 2h plus 10. Whoops. That should not be there because it was factored out. My bad. Good thing I caught myself before the catastrophe happens. And then with the limits, we direct sub. We directly sub in h is equal to 0, and we get the result is equal to 4x plus 10. Because this term in the middle, 2h, when we multiply it by h equals 0, that gets zeroed out. So the derivative of so this was equal to the derivative of our original function, which was 2x squared plus 10x. And honestly, if you've seen other methods of finding the derivatives, you'll see that like this definitely agrees with that. And to take the derivative like this, it all comes from the fundamentals of like we're trying to find the slope. So we're going to really zoom in. We're going to see like at a certain x value, and then we're going to add a little bit to it. Just go a little bit past that by h. But h, we want it to be very small. That's why we need the limit. We're going to take the slope, and that comes from the rise divided by run. We simplify to get this equation. This is also called the first principles method of finding derivatives. And once you find that, typically you'll be able to sub in your functions and solve and find your derivative. So that would conclude this question, and the answer that we have here on OneClass agrees with us. So we can mark that this question is good and keep it moving. Okay, just gonna clean off this whiteboard.